Okay, so up to this point, it is a natural question, given everything that we've looked at so far. Is it the Borel sets, right? Are the Borel sets going to be the sigma algebra that has been kind of the thing that we've been searching for, the thing that's going to be the restriction of M star down to just the Borel sets to allow us to measure sets? And it turns out, that's not a bad set. In fact, some mathematicians really just do take the Borel sets to be the measurable sets, right? But it actually turns out that there is an ever so slightly larger class of, shouldn't say it that way, it's not ever so slightly, but in any case, there is a larger class of sets that we call the measurable sets. Most mathematicians call the measurable sets. They don't really get you things that are that important, I guess, is the idea. Right, most of the time when you need to measure things, most of the things that you need to measure are Borel sets. So augmenting to this larger class of sets is, kind of going, in a sense, above and beyond the call of duty. But because it is possible to do this, and it does kind of arise in some natural ways, then we'll go ahead and do it. So these are called the Lebesgue measurable sets, right? We're going to define them in three different ways, right? The symbol that we're going to use for all of the measurable sets is this cursive or calligraphic L. And there is, right, so kind of historically it's interesting to know the way that Lebesgue came to understand these sets himself. And it is by sort of the same way that you kind of understand the Darboux integrals, right? So if you recall the sort of upper and lower Riemann integrals, or you could call them the Darboux integrals, we had like an upper integral, a lower integral, and we said that the integral exists, right? Just the integral full stop exists if the upper is equal to the lower. Well, that's similar to what Lebesgue understood the the measurable sets to be. He had this notion of an inner measure, right? We've been talking about the outer measure, but there's also an inner measure, and there's a very sort of strong analogy to the upper and lower integrals. And when they're equal, we get a measurable set, right? That's by definition. Now, we won't actually use this definition. For one thing, it's a little bit less useful than some of the other definitions. For another thing, it would require us to kind of talk about this inner measure. And I just kind of want to not do that if we don't have to. And there are these other things that we want to get to anyway that are, I would judge, more important. So we're going to just not do it that way. I just mention it for historical context and to kind of, it is kind of nice that you know how you could get yourself into thinking about these sets. So I like mentioning it just for that reason. But after you live with measurable sets, you study these things long enough, you eventually realize that they're equivalent to a different definition, and this definition is a little bit more useful. And the definition, we're going to prove, well, we're just going to accept each of these as a definition, and then prove that they're equivalent to each other. And these are going to be the things that we call the measurable sets. So this other definition is that we say that a set E is measurable, Lebesgue measurable, if there exists some Borel set inside of it, which is almost all of it. And by that I mean, when I say almost all of it, what I mean is that if you remove the Borel set, you get a set of measure 0, right? The parts of E that are not this Borel set is almost nothing, right? That's kind of the way that I think about that. Now, we will also see that this is equivalent to a set having this Caratheodory property, which this is much more abstract and harder to read. So that's kind of why I wanted to have this as one of our definitions, is because this makes some amount of sense still, and yet it's still useful. By the way, I call it the definition due to Axler just because I found, Axler defines it in his book on measure, integration, and real analysis. Maybe he got it from somewhere else. I haven't researched the history enough, so I'm just calling it the definition due to Axler. But anyway, so that's why I wanted to have this one here, is that it kind of makes sense and is useful. But this one doesn't make a lot of sense, right? I mean, if I try my best to read it in a sensible way, what I would say is that a set is measurable if it splits every set, or it splits the measure of every set, by which I mean that A has measure equal to the measure that's in E together with the measure that's outside of E. Why would we regard that as a good property or what we want from measurable sets? Why would we want to talk about those sets that split every set or split the measure of every set? It's not really all that clear. I mean, this does look a lot like additivity, so maybe you could kind of motivate it that way. But I think that's about the best I can do to motivate this. So why do I have it if it sort of doesn't seem all that easy to motivate? Well, it turns out that this definition is the definition that extends to other spaces, right? So eventually we're going to generalize the notion of measure to, not just real numbers, but, all kinds of other things. And when we want to talk about which sets are the measurable sets, those that satisfy this property are going to be the ones that we call a generally measurable set. So, so this one's kind of here almost just to be there when we need it to generalize the notion of measure. It's also useful, by the way. I mean, we will prove theory, right? Once we know that these two are equivalent and we can freely choose whichever one we want when we're talking about measurable sets, it will frequently be useful to use this one. So it's not like it's useless. So that's another reason to have it, is it's a useful property as well. So that's the plan, right? So this is here just for historical context. We're never going to use this one. This defines the Lebesgue measurable sets. So does this. And very shortly we'll prove that they are equivalent so that it is legitimate to have two different definitions of the same thing.